So this is a joint work with Max Kessler. We are both from ETH. I will devote the beginning of the talk to just explain what the task is, what is device-independent randomness amplification and privatization. Then I will show you our protocol and the results that we have for this protocol. Hopefully I will have a few minutes to say a few words about the proof technique, which is completely new, and end up with some open questions. Okay, so we already had several talks about randomness, so I don't need to motivate here. We use it in many different applications. Here we care about cryptography, and cryptography, many times we don't need just any randomness, but we need uniform private randomness. Okay, so the question that we are going to address in this talk is the following: can we create uniform private randomness from a weak public source of randomness? Okay, and to make it more interesting, we will actually restrict ourselves to use to start just with a single weak public source of randomness. Okay, so first of all, we need to understand this question better, so let's make sure that we all use the same terms. So when I say a weak source of randomness, I mean that the bits of the string, of the random string, can be biased and correlated with one another. There are two main models for these kind of sources, of weak sources. So the first one is the mean entropy source. This is just a source where we have just an upper bound on the most likely string of the source. And there is another type of source, a Santa-Vazirani source, SV source. This is a more structured source where we can think of the bits as a sequence of bits, one bit after the other, and each bit has some entropy condition on all of the previous bits. Okay, so this is Santa-Vazirani source. This is a source that we will concentrate on in this walk. Okay, next, when I say public, I mean that everyone can see the bits once they are produced. Okay, so we don't know them in advance up to this bias of the weak source, but once they are produced, then everybody can see them. For example, in the NIST randomness beacon, the numbers are just online, and we can all go to the web page and see them. Okay, so this is public. And then uniform and private, this is exactly the opposite, and it's always with respect to a quantum adversary. Okay, so we will have some quantum side information, and we will be interested in saying that something is uniform or private with respect to this quantum side information. Okay, so if we want to put this task in this picture, then we are looking for a protocol. This is this box here that will take a weak public source's input. This is the purple source, and will create a uniform and private randomness out of it. This is the green source. Okay. So which kind of protocol can we consider? So there are well-known results from classical cryptography or classical computer science in general that tell us that there isn't any classical protocol that can do this. Okay, then we can go to a standard quantum protocol where we just have, for example, photons and we measure them. But we all already know that once we go into the cryptographic setting, this is not really useful due to imperfections in the device. Okay, so if the photons or the measurements are not exactly as we expect, then it becomes much harder to prove that what we have is indeed close to a perfect private randomness. Okay, so this is why we go to the device-independent approach. Okay, so I will not go into the details and all of the introduction for device independence. We already heard several talks, but the idea again is to have, we're looking for some protocol. In this protocol, the honest parties will get these black boxes, which can be just some uncharacterized device, maybe even malicious. Okay, now the protocol will tell the honest parties how to interact with those boxes. Okay, and then the honest party can decide whether to abort the protocol or not, and if they do not abort, then they accomplish their task of creating the uniform and private bits. Okay, so this is what we're looking for this device-independent protocol. Okay, so let me say a few words about previous works. Okay, so Christopher already mentioned this morning, and maybe for those of you who are familiar with previous works, they all consider different models and they have different parameters, so I cannot just put them on one line and say this one is better than the other. So what I will do instead is to consider three parameters, which I think they're the most important ones, so just for the purpose of the talk. So the first one is a constant number of devices. So this is something that I want my protocol to have. What does it mean? It means that the number of the black boxes from the previous slide, I want it to be a small constant. Okay, why? Because if I now have a protocol with polynomial number of boxes, then obviously it means that in the experiment, you need to basically have polynomially many quantum labs that will implement this, and this is not realistic for a protocol. Okay, so I want a constant number of devices. The second thing is that I want my protocol to be truly robust to noise. So this means that even if in the quantum experiment we have a lot of noise, we still want to be able to construct a device such that the protocol will not abort with high probability. Okay, again, otherwise it's not useful, the protocol will always abort and we don't create anything. Okay, and the last property that I will consider now is the efficiency of the protocol. Okay, so this is how many random bits I'm creating using the protocol divided by the number of signals or the number of bits that I'm using from the source. Okay, so again, I want this to be non-vanishing, so non-zero efficiency. Otherwise, if I use many, many, many photons and I can extract only a single bit, then again, it's not very useful in the end of the day. Okay, so with respect to those parameters, this is where the previous works sit. Okay, so I will not get into the details of all of them, but you can see the advantages and disadvantages of each of them. One important thing here is, don't know if you can see it. So here we have an important work by Brandau et al. Okay, that achieves all of these parameters. So it's here in the intersection. But there is something important here. This, the model that they start with a private weak source. Okay, so this means that no one can see the source. The adversary also, after the protocol, we finished running the protocol, even then if something leaks, some information leaks about the initial weak source to the adversary, then our security is lost, okay, or might be lost. We don't have any guarantee regarding the bits that we created in the protocol. Okay, and our work lies here, so it achieves all of these properties while considering public source and any bias of the SV source. Okay. Good. So I'll tell you about our protocol and the results. So this is the setting that we consider here. Okay, so I'll explain together with the protocol. So this is our public SV source. Okay, and as I said, we can think of it as a sequence of bits coming one after the other. So let's say that there is this some point in time here, and all the bits, all the previous bits, this is what we call the history. Okay, so this includes all the past and maybe some other information, classical information from the history. Okay, and this is all classical information. And this is the point in time where the adversary needs to prepare the device and give them to the honest party, so to Alice. Okay, so the adversary at this stage, she knows the history. So when she prepares the box, these boxes can depend on the history. Okay, so this is why I have these lambdas on the black boxes. And of course, she can also keep some quantum sign information for herself. Okay, so this is the E. The E register is quantum, and it can also depend on lambda. Okay, so all of this depends on the history just because the history happened before. Okay, and then the adversary gives the device to Alice, our honest party. Okay, and now Alice can run the protocol. So what does the protocol say? Alice will take the next bits from the weak source. Okay, so these will be our inputs. And then she will use those inputs to interact with those black boxes, in particular to play a certain bell game many times, or to check a bell violation, whether those devices, they violate a bell inequality. Okay, so she gives the inputs, then the device, they create the outputs. And now Alice can check whether the statistics of the inputs and the outputs are fine for her, so whether they violate a bell violation, a bell inequality. Okay, so if the violation is too low, she aborts, otherwise we continue with the protocol. Okay, so the next stage of the protocol is to take the next bits from the source. Okay, so this is what we call our seed. And then Alice will apply a special type of extractor to both the outputs here and the seed. Okay, so this is just a classical function which is applied to O and Z, and this will create us our final secret randomness. Okay, the green string. Okay, and the most important thing here is that indeed we have this chronological order. Okay, so we first have the history, then we prepare the devices, then we use the inputs and the seed and so on. Good. So what is the statement of the result? It's this one. So what we show is that given any public SV source, there exists a device-independent randomness amplification protocol requiring only 2 devices, such that we have these 2 properties. So the first one is the completeness side. There exists an honest implementation of the device such that the protocol does not abort with high probability, even in the presence of noise. Okay, and the second part is the soundness. So it says that for any device, so malicious device, used to implement the protocol in the stated setting that I had in the previous slide, either the protocol aborts with high probability or close to uniform private randomness is produced. Okay, so this was the informal statement. Let me just state some quantitative advantages. Okay, so first of all, as was already stated in the previous slide, device requirement, we only need 2 components, okay, which is the minimal number of components, the minimal number of black boxes when using Bell inequalities. The robustness, so we can tolerate the maximal amount of noise. Okay, so as long as the devices are not effectively classical, as long as we can see a violation, it's possible to choose the parameters of the protocol such that we do not abort with high probability. And the extraction rate, so the efficiency of the protocol. So the specific number will depend on the specific extractor that we use in the last stage of the protocol, but it is possible to extract a linear amount of bits while maintaining cryptographic security for a large range of parameters. Okay, and maybe here just a small remark is that in the previous works that use a public weak source in the beginning, then I showed you that they all have a vanishing extraction rate. Okay, and it's important to understand that the vanishing extraction rate there was 0. It was 0 independently of the extractor that they choose. Okay, so it's not like the reason that we can make it here is because we choose a good extractor, and if you take it to the other protocols, then you fix it. So the problem with the efficiency was fundamental in the previous proofs and was independent of the extractor. Okay. Another quantitative thing that I can show you is, at least those who are familiar with randomness extractors, then you know that in order for the extractor to work, we need to have a guarantee of the mean entropy of the sources. Okay, so what we can do is to bound the mean entropy of the outputs from the box. So for any number of signals, so finite statistics, and any violation of the specific Bell inequality that we consider, and any bias of the source, we can basically plot these kind of values. We can calculate the amount of entropy rate that we can certify for the extractor. Okay. So a few words about the proof. So we need three parts in order to prove such a result. Okay. So the first thing that we need is we need a special Bell inequality that will allow us to define this protocol here. And this Bell inequality should basically accommodate correlations between the inputs and the box. Okay, so because we have an SV source, then those inputs can depend on the history, but the box also depends on the history. Therefore, we have correlation. This is not the case with the CHSH, for example. Okay, so in the CHSH game, we always assume that the inputs are independent of the box. Okay, so we need a special Bell inequality. The next thing that we need is we need a way to bound the entropy here, so to create those plots that I just showed you. And the last part is that we need a special randomness extractor here. So the important point to note here is that O and Z, so the output and the seed, they are not independent because they have this common past. Okay, so in particular, they both depend on the input and the history. Okay, and this is why we cannot just apply a two-source extractor from the classical setting, for example. Okay. So the Bell inequality, we use a relatively recent Bell inequality. It was developed by Putz et al. It's called the measurement-dependent locality inequality, and this is basically, it does exactly what we need. So it's a Bell inequality which already takes into account that the inputs and the boxes, they can depend on this lambda, on the history. Okay, you can imagine it as some kind of this line here compared to the CHSH. And what they showed is that for any bias, so for any such lambda such that we still have some randomness here, some randomness in X and Y, there exists a point here on the quantum set. So we can certify quantumness with this Bell inequality. What they did not show is they did not give any quantitative result that tells us how much randomness we can certify with the violation. So the first thing that we did was to say, yes, it's possible to certify randomness, and we proved those bounds that you can see here. So this tells us, given a violation, how much entropy we can certify from this violation of this particular new inequality. Okay, the next stage is to bound the total amount of entropy here. This we use the method that were developed last year in this entropy accumulation for the device-independent setting. On the high level, what we have in these works is basically a way to tell us, okay, if you know what is the amount of entropy from a single game, then you can have the total amount of smooth mean entropy. So we adapted the proof which we used here for QKD to this randomness amplification setting. So this is the plot from the previous slide for the single game, and then we get the entropy rate. And the last part is the quantum proof extractor. So we use also a recent work, quantum proof extractors in the Markov model. So these are extractors that allow us to extract randomness if the two sources are independent given some quantum side information. Okay, so in our scenario, we indeed have such a case. So the output and the seed are independent given the adversary side information, the inputs and the lambda. And with the entropy bounds, we can apply the extractor. So this is the security definition that Christopher mentioned in the morning. I will skip the details. Okay, so let me summarize. So what we have here in this work is a device-independent randomness amplification and privatization protocol that overcomes the drawbacks of all of the previous works. It's a completely new proof, okay? The fact that we overcome all of this means that this is basically the first protocol that we can possibly implement in a lab in the next few years, hopefully. Some open questions, how to improve this. Okay, so the first thing is that I'm pretty sure it's possible to get a better extraction rate. So the first place to look is basically to find a better single round bound. So you don't need to understand any of the security proof or the entire protocol. You just need to be able to find a better bound on the amount of entropy from the Bell violation of these MDL inequalities, or to find a new Bell inequality that will allow us to certify more randomness in this setting. The next thing that we can consider is an extension to a mean entropy source. So our work works for an SV source, not for a mean entropy source. And the last thing is whether we should consider quantum sign information about the source. So in my model, the E was quantum and the lambda was classical. It's not clear how one should think of a lambda which is a quantum, what it will mean exactly. But I think it's interesting to try to understand what it will mean and what we want it to mean, what will be relevant, and then try to extend the proof here. Thank you very much.